Okay, I'm going to continue with the exam 2 review where we left off. I may break this up into 3 videos depending on how much I get done in this one, because I do have class in less than an hour, so just trying to break it up so I can get it done and get it posted for you guys. So the last thing we did was this word problem here. Because it wanted us to find the maximum height of this object that is being thrown. And they gave us the form or the equation that represented the height of the ball thrown after t seconds. So this is a quadratic function. And so we said that to find the maximum height, or even the time that gives the maximum height, we had to find the vertex of this quadratic function, because that is where we get our maximum height, or the maximum value for that function, which in this case would be the height. Okay, but I want to back up a little bit and just go back and spend some time on these properties here. So let me erase some of this so we're not getting mixed up. Okay, so remember we learned all those properties of quadratic functions, and I gave you this equation, or the form of the ordered pair, to find the the vertex of a parabola. And a vertex of a parabola could either be a maximum or a minimum value. So if it's opening up, it has a minimum value, and if it's opening down, it has a max value. And the axis of symmetry, it was that vertical line that goes directly down the middle of the parabola. So that was always equal to the x-coordinate of the vertex. So x equals the negative b over 2a. So of course, we have talked about how when a is positive, then our parabola is opening up. And I have that parabola drawn right below that. And so therefore, this parabola will have a minimum value at f of negative b over 2a. And this represents the y value of that vertex. And if a is opening up, our function, we know, will be increasing from the x value of the vertex, so negative b over 2a, to positive infinity. And it'll be decreasing from negative infinity to negative b over 2a. That's always true. Remember, we've seen that pattern when we were doing problems with these in chapter 3. So it's increasing on the right there, it's going up, and that always starts at the x value of my vertex, so negative b over 2a. And then it's decreasing on the left side. So that always starts at negative infinity and goes up until the x value of my vertex. And then the other case is when a is negative, the leading coefficient is negative, then our parabola will be pointing down, and we will have a maximum value at our vertex. And that will be the y value of the vertex. So that's the notation for the y value of the vertex, because the negative b over 2a is the x coordinate, and you plug that into the function to find the y coordinate. So this, in this case, the function will be increasing from negative infinity to negative b over 2a. So they switch, because now it's increasing from on the left, but it's decreasing on the right now. So that would start at negative b over 2a and go to positive infinity. And of course, the domain of both of these is just negative infinity to infinity. And the range of the first case, when we have our parabola opening up, will always start at the y value of our vertex and go to positive infinity. And when the parabola is opening down, the range will start from negative infinity and go up to the y value of our vertex. So if you can remember, or if you understand what this means, you can just put this on your flashcard. So just knowing the vertex of a parabola tells us a lot about it. Okay. So let's do an example here. It says find the vertex and determine whether the function has a minimum or maximum value. State the value, find the range, domain, and intervals for which the function is increasing or decreasing, and find the axis of symmetry. So first, we know that a is equal to negative 2, which is less than 0. So that tells us that my parabola is pointing down, which means I will have a maximum value. At the vertex. So let's find the vertex. The entire point, the ordered pair, is given by negative b over 2a. That's the x-coordinate. And then we can find the y-coordinate by plugging that answer into our function. So negative b over 2a is equal, b is negative 4. So this would be negative and then negative 4. So it's a double negative. And then 2 times a, which is negative 2. So the top becomes positive 4 and the bottom becomes negative 4. And this would be negative 1. So this is the x-coordinate of my vertex. And then we can find the y-coordinate by plugging that value we just found, which is negative b, into my function. So this would be negative 2 times negative 1 all squared minus 4 times negative 1 plus 1. Negative 1 squared is a positive 1, and positive 1 times negative 2 is negative 2. Negative 4 times negative 1 is plus 4, and then bring my plus 1 along. Negative 2 plus 4 is 2, plus 1 is 3. So this is the y-coordinate of the vertex. So therefore, my vertex is equal to the point negative 1, 3. And this means, well, this helps us find the maximum value. We already said it was going to have a maximum value, and the maximum value is always the y-coordinate of my vertex. So the maximum value is equal to 3. And then let's just sketch a little quick general shape of my graph. The vertex is at negative 1, 3, 1, 2, 3. So there's my vertex. I already know it's pointing down because a is negative. So I know it looks something like this. Not perfect, but I know it looks something like this. So therefore, I can determine my range. The range would be from negative infinity up until positive 3, which is the y-coordinate of my vertex. And that would have a bracket because it's included on that function. Of course, the domain is all real numbers, or negative infinity to infinity. And the intervals for which it's increasing and decreasing comes from the x-coordinate of my vertex. So it's increasing on the left because it's going up, up, up until that x-coordinate. So that would be from negative infinity to negative 1, both with parentheses. And then it's decreasing on the other side, on the right side of the vertex, which starts at negative 1 and then goes to positive infinity. And then the axis of symmetry is the vertical line that goes through the vertex, which is equal to x equals the x-coordinate of my vertex, which is negative 1. Okay. So just by finding the vertex, we were able to answer all of those questions. Now, I already did number 8. That would be in the last video if you want to go back and watch it. Okay, number 9 wants us to find the zeros of this quadratic function. So remember, to find the zeros, you set the entire function equal to 0. So I'd take w squared plus 11w plus 28, and I set it equal to 0. And then I solve. And this is a quadratic equation. So we can try and factor it by finding two numbers that multiply to give me 28 and add to give me 11. And that would be positive 7 and positive 4. 7 times 4 is 28, and 7 plus 4 is 11. So now I take both of these factors and I set it equal to 0. And then I solve each one. So w would be equal to negative 7, or w would be equal to negative 4. So these are the zeros, which are the same thing as the x-intercepts. And the x-intercepts come in the form of a point. So it'd be negative 7, 0, and negative 4, 0. Just wanted to remind you of that. Those are my x-intercepts. These are my zeros, which are the same thing. Okay. So that's for quadratic functions. Now, we also learned in chapter 3 how to solve rational equations. So I'm going to review that here. So to solve a rational equation, first we multiply each term by the LCD. And then to clear the fractions. And then we'll solve the remaining equation like normal. And then you have to remember at the end to check your solutions, because this rational equations, they have restrictions. Can't divide by 0. So if you get an answer for x that makes any of those denominators equal to 0, then it will not be in your solution set. You have to exclude it from your solution set. All right, so to find the LCD, the first thing we want to do is write this whole thing where with all the denominators being factored. So the first denominator already is factored, x minus 2 can't be factored anymore. The second denominator, same thing, x plus 2 can't be factored anymore. But the last one is a difference of 2 squares, x squared minus 4. And so that factors to x plus 2 times x minus 2. So the LCD here is x plus 2 times x minus 2. Because they all have those in common. So now I'm going to multiply every single term by the LCD. So when I do this on the first fraction, the x minus 2's will cancel, and that will leave me with 3 times x plus 2. And then the second fraction, the x plus 2's will cancel, and that will leave me with x minus 2 times 1, which is just x minus 2. And then on the very last one, they will all cancel, and that will just leave me with 10. So now I continue to solve like normal. I'll distribute the 3. That will give me 3x plus 6. Bring down the plus x minus 2 equals 10. Combine like terms. 3x plus x is 4x. 6 minus 2 is 4. Oops. Then subtract the 4 over. And then divide both sides by 4. So x equals, if I divide 6 and 4 both by 2, that will give me 3/2. Now, again, you'll want to check this. By plugging it into the original and making sure that the denominators won't be 0. But the only thing that will make those denominators 0 would be 2 or negative 2. So we're good there. This would be the correct answer. But you want to make sure you check that. Okay. All right, the next type of equations we learned how to solve was radical equations. And the first thing we did to solve radical equations was to isolate the radical on one side, so get it by itself, and then raise both sides of the equation to the power of the root. And then you need to make sure that you check your answer at the end to make sure that it is in fact equal on both sides and that you don't get a negative under the square root. So if you do, then we will exclude that solution. So this example, the square root's already by itself, so I'm going to go ahead and square both sides. So that will leave me with x plus 2 equals x plus 2 times x plus 2, because I need to FOIL it. So on the left side, it cancels my square root, but on the right side, I need to FOIL that x plus 2. So when I FOIL, I get x times x, which is x squared, plus 2x, plus 2x, so that would be 4x after I combine like terms, and then plus 4. And now this is a quadratic equation, so you want to get everything to one side to get it equal to 0. So we'll subtract x from both sides, and we will subtract 2 from both sides. So 0 will be equal to x squared plus 3x plus 2. And this will factor to x plus 1 times x plus 2, since 1 times 2 is 2 and 1 plus 2 is 3. And then we will set each of these factors equal to 0. So x will be equal to -1, or x will be equal to -2. So now we need to check. So we're going to check both. So x equals -1 first, and then x equals -2. So when I plug -1 into the original, I get the square root of -1 plus 2 equals -1 plus 2 on the right side. And on the left side, -1 plus 2 is 1. So that leaves me with the square root of 1, and then -1 plus 2 on the right is also 1, and the square root of 1 is 1. So this is true. It did not give me a negative under the square root, so we're good. So x equals -1 is part of my solution. And then for the other one, we're plugging -2 in for x, so that would be -2 plus 2 under the square root equals -2 plus 2. Well, -2 plus 2 is 0. The square root of 0 is 0. So that one also works. We can have the square root of 0, that's fine. So both of these are solutions, but you need to check, because if it would have been false, that would have not been part of your solution. Okay. And then the other type of equations that we learned how to solve was absolute value equations. And so to solve an absolute value equation, the first thing we do is isolate the absolute value and get it by itself. And then we use this rule to form two separate equations. So once it's by itself, the absolute value of some expression equals some number a. As long as a is positive, then we would have the expression x in the absolute value equal to a or equal to negative a. So this is how we set up our two equations. Remember, if it's equal to a negative, if the absolute value of x is equal to a negative a, then it's no solution. The number is negative. Okay, and again, this x in here can be anything. It can be a full expression just like it is here. It doesn't have to be just x. We want to get just the absolute value by itself first. And if we get the absolute value by itself and it's equal to a negative number, then it's no solution. So for this example, I'm going to get the absolute value by itself by subtracting 3 to both sides. So I would have the absolute value of x minus 2 is equal to 2. And now I have the absolute value by itself, so I can separate it into its two equations. I would take all of x minus 2, set it equal to that positive 2, or x minus 2 equals negative 2. And then solve both of these. So I add 2 to both sides. So x is equal to 4, or add 2 to both sides here, x is equal to 0, because negative 2 plus 2 is 0. So these are my two solutions. And with absolute value equations, it's not mandatory for you to check. There's no restrictions, but you can just to check to make sure you did your work correctly. Okay, and then we also learned how to solve inequalities that had absolute values in them. And I gave you that whole list of rules for that. I'm going to remind you of them here. So if, and you can put these on your flashcard, by the way. So the first one is if, oops. There we go. Okay. The first one is if we have the absolute value of x less than a number a, and that number would be positive. When it's less than, I told you to take the expression inside the absolute value there and put it between the positive a. So you write x is less than a, just like it said over here, and then same sign, and then negative a on the left. And if it is greater than a, then we take that x and set it greater than a, just like it says. Or we take the x and we set it less than negative a. This should say negative a. And I'm using the wrong. So on the negative version, we have to flip the sign there. And then I also gave you two more rules about this whenever a was a negative number. When a was less than 0, If the absolute value of x is less than a, this would be impossible because a would be negative, and there is not an absolute value of any number that's less than a negative because it makes it all positive. So this would be no solution. But if a was negative and the absolute value is greater than a, this would be all real numbers, because all of them would be positive, which would mean that no matter what I plug in for x, that would be greater than a negative number. So this is when a is less than 0, negative. Okay, so 13 says solve the following inequality and write interval notation for the solution set, then graph the solution set. So this one, the absolute value is already by itself, so we can go ahead and use one of those rules. And we have that the absolute value of 3x here is greater than or equal to 12. 12 is positive, so we are in this second case over here. And it's greater than, so I just take the 3x inside the absolute value and I set it greater than or equal to 12, just like it says. Or I take 3x and I change the sign to less than or equal to negative 12. And then I would solve both of these inequalities for x. So I would divide both sides by 3 on both of them. So x will be greater than or equal to 4, or x will be less than or equal to negative 4. And so if we graphed this solution set, we would have the numbers negative 4 and positive 4. Both of these can equal because it has the or equal line underneath the inequality symbol. So they would get a closed circle or a straight bracket. And for x is greater than or equal to 4, that would be a bracket and shading it to the right, because that would be everything greater than 4 would be to the right. And for x is less than or equal to negative 4, that would be a straight bracket and shading to the left, because that is everything less than or equal to negative 4. So an interval notation this would start from the left of my blue shading all the way at negative infinity, and it would go to negative 4 with a bracket. And then I would have my union symbol to combine the other interval, which would start at positive 4 with a bracket since it's included, and go to positive infinity. So that would be my answer in interval notation, and the graph on my number line would be the answer using the graph. The next one is the absolute value of x minus 3 less than 5. So in this example, the absolute value is already by itself again. And so, and it's less than a positive number. So that's going to be the first case up there. So when it's less than, I take the expression on the inside of the absolute value, which is x minus 3, and I put it between 5 and negative 5. So on the right, I would write less than 5, just like it says here. And on the left, I would put the same direction of that symbol and then put negative 5. So I'm putting that x minus 3 in between -5 and 5 when I do that. And then I solve for x in the middle. So I add 3 to all 3 sides to cancel it in the middle. And that will leave me with x is less than 8 or greater than -2. So for the graph on a number line, I would have these two numbers, -2 and 8. Neither one of them can equal for -2 or 8, so they would have parentheses. And then it says it's in between, so I have to shade in between these two numbers. Because this means that x is less than 8 and it's greater than -2. So all the numbers within that shaded blue region is true for that inequality. And then for the interval notation, this would just be a parentheses from -2 to 8 with a parentheses, because that's what's being shaded. And so that would be it for that one. All right. And then, so that was everything from chapter 3. And now this starts chapter 4, which was all about polynomial functions. So I put this chart here for that end behavior that we learned about. So this is probably the most recent thing we've learned about. So hopefully that's fresh in your memory. If the polynomial has a highest exponent that's even, so the degree is even, and the positive or the leading coefficient is positive, then we know that the end of the graphs are both pointing up. Even degree, they're doing the same thing. Positive, they're pointing up, they're smiling, they're happy. But if it's an even degree and negative leading coefficient, then they're both pointing down. So an example of the first one would be like 2x squared. Well, actually, let me do this. 3x squared minus 4x. That one has even degree of 2 and positive leading coefficient of 3. And the one on the bottom could just be -3x squared minus 4x. Now my leading coefficient is -3, but my degree is still 2. And then when we have a odd degree, then our function is going in different directions at the ends. And if our positive or our leading coefficient is positive, then it should be going up towards the right. So it ends by going up in the positive direction, which means the first one is going down on the left. And if we have a negative leading coefficient, then it should be going towards the bottom. It should be decreasing towards the right, which means it's increasing towards the left. So an example of this would be 5x cubed plus 5. And this one would be -5x cubed plus 5. Those are just little examples. All right, and then we also learned about multiplicity of zeros. So remember, once a function is in its factored form, then c is the 0, because c minus c makes that 0. And k is the multiplicity. So it's really just, the multiplicity is how many times a factor of a 0 occurs. So, for example, if I had x minus 2 times x minus 2 times x minus 2 times x plus 1, well, this factor occurs 3 times. So the 0 is 2, because that's what makes that equal to 0. And the multiplicity would be 3, because it's occurring 3 times. And that can be written as x minus 2 all cubed. Okay, so if we have an odd multiplicity, the 0 of that factor will cross the x-axis. But if we have an even multiplicity, then the 0 of that factor will bounce. Or you could say will touch the x-axis and then bounce off. So it doesn't actually cross. It just goes, it touches at that point, and then it goes back in the direction it came from. All right, and then we learned that the maximum number of real zeros, or x-intercepts, that a polynomial can have is equal to its degree. And the maximum number of turning points would be the degree of the polynomial minus 1. Highest exponent minus 1. So let's see some examples. Number 15 says, for the function below, provide a sketch of the end behavior of the graph, then give the number of maximum zeros, x-intercepts, and turning points of the function. So for the end behavior, we use the leading term test. The leading term here is the one with the highest exponent, the largest exponent. So that would be negative x to the 7th power. So the leading coefficient is negative 1. It's the number in front of x to the 7th. And the degree here is 7. So the degree is odd, which means our end behavior is going in different directions. And the leading coefficient is negative, which means towards the right it should be going down, which means to the left it's going up. So that is what the end behavior of this polynomial would look like. And then the number of maximum zeros is equal to the degree, which is 7. It's the largest exponent. And this is the same thing for the number of maximum x-intercepts, since they are the same thing. So this is also equal to 7. Zeros and x-intercepts are the same thing. And then maximum number of turning points would be 7 minus 1. Which is 6. Okay. And so you'll have a question like that on the exam for sure. Well, most of these that I'm doing, there will be on the exam. So, but this one's not too bad if you know these rules. And then I think I'll stop there. I only have 2 pages left, but I do have class soon, so I don't want to run out of time. Actually, let's just do number 16 real quick. Okay, so for 16 it says for the polynomial function below, find the zeros and state the multiplicity of each zeros, then graph the function. So for this one, this function is already factored. So it's already factored. So I don't have to worry about that. So to find the zeros, it's just what makes these factors here equal to 0. The -2, by the way, is just a constant out here. I'm not worried about that because there's no x value out there with that -2 that I can plug in to make that 0. So the zeros are going to be what makes x minus 1 0 for x? Well, that would just be 1. So if I plugged 1 in there, 1 minus 1 is 0. And all 3 of these are the same. So I only need to write that one down once. And for the x plus 3, what makes that equal to 0 would be -3. So there's only 2 zeros here. Okay. And this is the same thing. This can be rewritten as -2 times x minus 1 cubed times x plus 3, because that x minus 1 occurs 3 times. So for the next part, it says the smaller 0 has a multiplicity of what? So the smaller 0, they're referring to the -3, because -3 is smaller than 1. So the multiplicity of that 0 is just 1, because that's the exponent on that factor. It only occurs once. But the larger 0 has a multiplicity of 3. The larger 0 is 1, by the way. But the multiplicity would be 3, because that's how many times it occurs. Okay? So let's plot these zeros. There would be 1 at x equals 1 and 1 at x equals -3. And we know that because the multiplicity, both of them are odd, both these multiplicities are odd, so both will cross at these x-intercepts. Both will, not with, will cross. And then to finish graphing it, we will definitely need to know the end behavior. So we need to know the leading term. So if we look at this version here where I rewrote it, I know the -2, if I multiplied all this out, -2 would definitely be my leading coefficient because there's nothing else in front of the 2 x's in there. So -2 will be my leading coefficient. And then from the first factor, I have x minus 1 cubed. So if I multiplied that out 3 times, that would give me x cubed. It's the leading term from that factor. And then the last one, I still have an x in there. So I would need to multiply by 1 more x. To get my leading term. Let me rewrite this, sorry. So this would be negative 2x to the 4th power. So my leading coefficient is negative 2, which is negative. And my degree is 4, which is even. So my end behavior is doing the same thing since the degree is even, and they're both pointing down because the leading coefficient is negative. So I know from these two x-intercepts, they would both be pointing down, something like this. And then from the multiplicity of both of these zeros, I know that they're both crossing. So this one will come up, and then it has to come back down eventually. And so it'll look something like this. And if you were graphing this on Pearson by hand, you would just want to find one more point. Between the two x-intercepts. So I'm going to pick 0. I'm going to find f of 0. Plug 0 in, so that'd be negative, and this would also be my y-intercept. So this would be negative 2 times 0 minus 1 cubed times 0 plus 3. 0 minus 1 is negative 1. Negative 1 cubed is negative 1. Negative 1 times negative 2 is a positive 2. And then I would have 2 times positive 3, which is 6. So this is actually going up higher than that. It's going up to, here's my y-intercept. So this is going up some and then going back down. And you should be able to plot that on Pearson just by using that information. Okay. Now, the last part of this review I have here is about the rational functions. So if you just watch the the video 4.5 part 2, I do a lot of these examples. So you can go and watch that video for that review. That's what we just finished. So hopefully that'll be fresh in your mind. But again, I have a lot of examples that I did in the 4.5 part 2 video on these. So you can use that to review. Other than that, that is it. So I will post this, and you guys hopefully will take your practice exam and study. If you have any questions, just send me an email. If you need to meet with me during my office hours, or even you want to schedule a Zoom before you take the test, just let me know. All right, you guys have a good day.